All right, so what could go wrong with integrating factors? Now, I've already written the problem. The reason why is October is hunting my notes. She will eat it. She will sit on it. We don't have the notes for this video, so I have to write this before the video. We're going to solve a very similar differential equation. Again, what's the difference? Well, it's kind of hard to see the difference right now. Let's put it in that standard form. Let's subtract this part over. Right, we have dy dt minus t squared times y equals t minus 1. So very similar. Right? In fact, the right-hand side is the same, that b of t function. It's just instead of dividing by 2 over, or multiplying by 2 over t, we're multiplying by negative t squared. Seems easier, right? I'm sure it will be. Okay? And again, we can find the homogeneous, the solution to the associated homogeneous differential equation. We're going to run into some issues if we try to guess and check. You're welcome to find it. I don't think you're going to succeed because the solution to this differential equation is pretty special. But if you do succeed, I'd love to know about it. So, it looks relatively nice. Let's find our integrating factor. So we know the integrating factor is mu of t is equal to e to the integral of this g dt, which is going to be e to negative 1/3 t cubed plus a constant. I don't know. Whatever constant you want to use, I'm going to use c equals 0 or k equals 1, depending on how you look at it. Great. Simple integral, no problem. Easy integrating factor. And then I'm going to multiply both sides of this equation by my integrating factor. And we're going to get e to the negative 1/3 t cubed times dy dt minus t squared e to the negative 1/3 t cubed times y equals e to, oh gosh, I'm running out of room. I thought this would go a little better. This is not supposed to be the problem. E to the negative 1/3 t cubed times t minus 1. All right. And so whenever we do this, we should really always check, especially in step 3. Let's always check that we actually are using the product rule. Don't just assume. All right. We should always have d dt is equal to that mu e to the negative 1/3 t cubed times y. We should always have this. But it's really good practice to make sure that we found our integrating factor correctly. If we use the chain rule here, do we actually get this? If not, you messed up in your integrating factor. And I, of course, would never make a mistake, so I never need to check. But if I did, what would I do? Derivative of the first thing, that's going to be itself times negative t squared. Ah, great. We have itself times negative t squared and the y. Plus itself times the derivative of y, which is this term. Great. I did it right. Good job. And now we just integrate both sides. So when we integrate the left-hand side, that's easy. E to the negative 1/3 t cubed times y. And the integral of the right-hand side, integral of e to the negative 1/3 t cubed times t minus 1. We could split this up into 2 integrals if we wanted. The problem is that both of those 2 integrals are garbage. U substitution will not work. Integration by parts will not work. You might be able to get one of them with integration by parts, but I don't think so. You certainly won't be able to get both of them with integration by parts. So, in fact, this integral right here, and again, we'd have to multiply this over, blah, blah, blah. This integral right here actually cannot be solved like by hand. It cannot be expressed in terms of elementary functions. So like there is a solution that introduces the gamma function, but you're not doing this by hand. I think I may have written my gamma wrong. It's been a while since I've written gammas. The gamma function, it can be used to model this, but again, that's not an elementary function. It's pretty messy, and again, it's kind of a little self-referential, and we use computers to evaluate that. So we can use a computer to evaluate this integral in a sense, but we can't do it by hand, so we're a little sad. Or maybe you're happy because you're like, I can't go any further with this method. So again, this is a type of problem. And again, anytime you're dealing with integrals, you have to just be okay with there's going to be 99% of these you just cannot do. Derivatives, we can take the derivative of pretty much most functions. Integrals, we can only take a derivative of this many functions. Differential equations, we can only solve this many functions or this many equations, okay? So again, in a math class, of course, I give you a bunch of integrals that you can solve, but realistically, there's so many integrals that we cannot solve. But again, we get practice. We work on things to get a better understanding, a deeper understanding of calculus, which is why we do those things. Okay, so that's pretty much it. Again, I think, yeah, that's all I wanted to talk about. 6-minute video. We need more of those. Anyway, enjoy. Ask me if you have questions. And in the next video, we'll get into more applications with a cool mixing problem. I love mixing problems. And we're going to talk about dumping trash in a lake. Okay?